Well, thanks a lot, Sebastian, for inviting me to give this presentation. Thanks to all of you for attending my talk. So the title of my talk today is Equal Risk Option Pricing with Deep Reinforcement Learning. And this is joint work with Alexandre Carbonneau, who is my former PhD student and who now is working at Morgan Stanley. So yeah, let's get started. So the topic of this presentation is option pricing, but pricing that is consistent with hedging procedures, and where we're going to use reinforcement learning to determine the price of the option. By the way, if you have questions, anytime, feel free to stop me. I'll just answer to your question. Okay, so feel free to interrupt me. The content from this presentation is drawn from 3 different papers that are displayed here. The first one, which was published in Quantitative Finance, and the other 2 ones, which are working papers available on arXiv. So a bit of motivation: if we consider a complete market setting, then it's possible to replicate any derivative with a replicating portfolio, and the pricing is trivial in that case because the price of any derivative is simply the price of the replicating portfolio. But in practice, markets are incomplete, and there's no perfect replicating portfolio. So whenever you apply hedging, there's always some residual risk. So then it's not trivial to determine a price for the derivative. So how can we determine the price of such derivative? So a bit of literature review here. The most common way to do that is through selecting a suitable martingale measure. So there are multiple criteria to decide on a martingale measure to be used. So some equilibrium models lead to some martingale measures, such as the Escher transform. You also have a model invariance criterion, where you just use a mean correcting procedure to change the drift but leave the structure of the model intact. Or you have a minimal perturbation or minimal entropy martingale measures that you can use. So there exists a plethora of martingale measures that you can use. But in this case, one issue is that the hedging procedures, such as delta hedging, they're a byproduct of the pricing, but the pricing is not necessarily made to be optimal with respect to the hedging procedure. Okay, so we would like to propose methods where the pricing is consistent with optimal hedging. So there were approaches that were proposed in the literature for that. So quadratic hedging methods have been proposed, such as local risk minimization, the extended Gersonov principle, which are kind of local hedging procedures, or there's the variance optimal hedging from Schweizer 95, which uses a global criteria and optimizes risk throughout the entire lifetime of the derivative. So in this case, the price of the derivative is simply the initial value of the optimal replication portfolio or optimal hedging portfolio. Now, there are issues associated with these methods. The first one being that these methods, they rely on a quadratic penalty. So if you're a hedger and you apply this and you use a quadratic penalty, you're penalizing gains, which is undesirable behavior. We'd like to have a procedure which does not penalize gains. Second, the prices associated with these methodologies, they're not necessarily arbitrage free. Okay, so the martingale measures, associated martingale measures, are often sign measures, and prices can be negative, which is at least a theoretical issues. And a third issue is that we consider that the same hedging procedure or strategy is used both for the short position hedger and the long position hedger, whereas in practice they might use different trading or hedging strategies to hedge the different positions. So other methods were proposed to remedy these issues. Some of them are based on utility indifference pricing. So you can find the price of a derivative as the value which makes an investor indifferent between including or excluding the option from his investment portfolio. Or there's another version of this approach, which is instead called risk indifference instead of utility indifference. So these are great methods. But again, there's an issue associated with these, is that the price might be different if you consider hedging a long strategy or a short strategy. Whereas in practice, if you want to trade an option, you need a unique transactional price for both the long and the short position. Okay, so we'd like a method which addresses that issue once more. So the work we propose relies on this original framework of Guo-Zhu, which is called equal risk pricing. The original paper is displayed there. And the idea here is that we're going to have two agents, one hedging the long position, one hedging the short position, and we'll define the price as being the initial value of the hedging portfolio, or the option premium, which will be such that the residual risk for the long position will be the residual risk for the short position. So in terms of risk, the investor should be, or the, let's say, market maker who like purchases and hedges, or like sells or purchases and hedges his position, should be indifferent between holding a long and a short position in terms of risk. There are ways to generalize this. So we consider equal risk, but in practice, it might be more desirable to have equal risk-reward framework, because if both positions have equal risk but non-equal profitability, the agent might not be indifferent between hedging the long or short position. But for simplicity, let's only consider risk here, and we assume that the price is set as the value of, or for the option premium, which makes residual risk equal for both the short and long positions. Okay, so what are the advantages of this approach? Well, first, we have a single price for both the long and the short position. Second, this methodology produces prices that are consistent with optimal hedging methodologies. And also, it's quite flexible because it allows for the quantification of risk through several types of risk measures. So you don't have to rely on the quadratic penalty. For example, you can use convex risk measures, such as the CVAR, expected penalties, etc. So it's a framework that is quite flexible. So this might be another advantage of the approach. Okay, so these are the advantages. Now, what are the disadvantages? It's that it's not trivial to compute the solution. Okay, so it's a complex problem to solve for equal risk prices. So you need to rely on numerical techniques, and this is what has been done in our papers. We relied on reinforcement learning procedures to come up with the solution of the option pricing problem that we will describe shortly. Okay, so you can use reinforcement learning, or you could also use dynamic programming procedures to solve these, but we relied on reinforcement learning. And we had a scheme which kind of resembles the scheme from the Buehler paper, the deep hedging paper, but with small modifications to the numerical approach. Okay, so let's describe a bit the mathematical setup of our work. We consider a discrete time market where here the time steps are t0, t1 until tn, so it's a discrete time setting, and we assume that we have several assets, liquid assets, that can be traded on the market. So the first one is a risk-free asset, which we assume grows exponentially at the deterministic risk-free rate. Of course, we could have stochastic interest rate, that can be done too, but for simplicity, let's assume a constant risk-free rate and deterministic risk-free rate. And we can assume we have the risky assets that can be traded. So for example, these can be underlying assets of the options, they can be other options, etc. And we will want to price a derivative whose payoff at time here, at this time, capital T here, is given by this. So let's consider, without loss of generality, a European put option, but of course this methodology can apply to a vast number of other derivatives. Okay, but for now we consider a put option on whose underlying asset here is S1, the first of the risky assets in the market. Okay, so to do that, we'll consider self-financing strategies where we set up a hedging portfolio initially, and on each time step, the portfolio can be rebalanced, and at the end, we hope that the hedging shortfall between the derivative payoff and the final value of the portfolio isn't too large. Okay, so what do we mean by self-financing? I guess most of you are familiar with that, but it means that there's no injection or withdrawal of capital from the portfolio except at the onset or at the maturity. Okay, so let's now define what is the mathematical problem that we're trying to solve to get the equal risk price. So we'll consider two mathematical problems to do so. So here, the hedger of the short position here will attempt to minimize across all possible trading strategies. And trading strategies, it's the dynamic allocation to the various assets throughout the duration of the hedge. Minimize across all hedging strategy. The risk, rho, stands for a risk measure associated with the hedging shortfall at the maturity for the short position. So the payoff of the derivative, which needs to be paid, minus your terminal portfolio value. So this is for the short position. And conversely, for the long position, you solve a similar problem. So you attempt to minimize across all possible trading strategies the risk associated with your terminal shortfall. But instead, the difference here is that you have a minus sign here, because if you're the long position, you're going to receive the payoff instead of giving that payoff. And we see that these two problems, the solution is a function of V0 here, which is the initial value of the hedging portfolio. Okay, so depending on your initial value of the hedging portfolio, you might have different trading strategies. Okay. Yeah.
What was the Zn again?
Oh, sorry. Okay, so this I forgot to tell, but Zn might be other information. So if you're, because we use a put option, but in some papers we hedge, like for example, Asian options or things like that. So they can be running averages. So I forgot about that. This was a slightly more general, but yeah, Zn is other variables that might impact the payoff. Okay, and now what about this V0? What we're going to assume is that V0 for the short position is the option premium, because when you sell an option or write an option, you receive the premium, so you can use that as your initial portfolio value. And conversely, for the long position, it's the opposite. You need to pay that premium initially, so we assume that the initial portfolio value V0 is minus the option premium. So the equal risk price in that context is set as the value C0 star, which equates the terminal risk, terminal hedging risk for the long position and the short position. So this is the theoretical definition of an equal risk option price. Okay, so what risk measures can we use? There's, again, a plethora of measures that we can use. In the literature, some people suggest for that setting convex risk measures, which have these properties. And one property that is very useful in this context is the second one here, translation invariance, which assumes that if you translate your wealth by a constant, then your risk is reduced by that constant. Okay, so examples, well, a very famous example of this is the CVAR, conditional value at risk, that people can use for that. There's well, yeah, exactly. Or what some other people use, for example, the Bueller paper, they tended to rely on these expected penalty metrics, where you have, instead of being the expected shortfall, it's the expected shortfall weighted by some penalty function. So an example of penalty function we can use is the order P polynomial, but only if you have a loss, and you can set it to 0 if you have a gain, to avoid penalizing any gains from your portfolio, which is a desirable outcome. Okay, so depending on what risk measure you use, you can have some simplification. So if you use convex risk measures, it's possible to show the following. It's possible to show that the equal risk price here can be obtained simply through running through finding the strategies, optimal strategies for a single initial portfolio value that you could select as 0, and you can show that the equal risk price can be obtained by this formula here. So you only need to solve the problem for one single value of the hedging portfolio, and you get the solution here. Okay, and another byproduct of this method is the optimal hedging risk here that you obtain once you've identified the equal risk price. And this metric here, the optimal residual risk, can be seen as some form of measure of the market completeness. So for various derivatives or various markets, you can assess how hard is it to hedge a derivative in this market. So is it very complicated, or you could hedge very well and not have a lot of risk? And that could be useful, for example, if you're risk averse and you want to adjust prices. So I feel this epsilon metric is a useful byproduct of the methodology that is proposed. Okay, so this is the theoretical framework. Now we'll talk a bit about the the numerical approach, because the hard part is the computation of these prices. Okay, we don't have any closed form, so we need numerical methods to tackle these kind of problems. Okay, and these are optimization problems, and because you have a sequence of rebalancing to optimize, it's a sequential decision problem and a feedback sequential decision problem where each of your decisions or rebalancing must take into account the contemporaneous information available on the market. So these settings, sequential decision processes, they can be tackled with tools of either dynamic programming or reinforcement learning. And in the papers, we use a reinforcement learning setting. And in reinforcement learning, there's kind of two streams of approaches. Some learn a so-called value function, some other learn directly the policy. We relied on deterministic policy gradient methods where we directly learn the policy without going through learning a value functions, for those who are a bit familiar with that area. Okay, so this is like in the deep hedging paper, they learn directly the policy instead of learning a value function to get as a byproduct the optimal policy. So a bit of illustration, how is it done? Well, to get the optimal policy, of course, we have there's an infinite possible values for the state, so we need to rely on some approximation. And the idea here is that we will use a neural network to approximate the policy function. Okay, so the idea here is that the optimal allocation to the various risky assets here on any time point, they will be function of variables or contemporaneous market information. So if you assume, for example, a Markov setting, you can show that the optimal hedging allocation to your various assets will be a function of n, which is equivalent to how much time until maturity is left. What are the values of the various assets, especially of the underlying asset? Vn here is the current portfolio value. So if you've accumulated a lot of hedging gains, you might not behave the same way if you're in a shortfall, let's say. And finally, In here is a set of other information. So it can be market volatilities for the various assets, or for example, the random variable Z, which includes running average or running maxima if you're hedging Asian options or look back options, and etc. So the idea here is that the optimal strategy is a function of all these variables, and what we'll do is simply to approximate this function with a neural network. So the idea here, the optimal action on any time point is a function of these variables. Well, we'll assume that this function will be well approximated with a neural network, so a parametric function of theta, theta being all the weights and biases within the neural network. So now the optimization problem boils down to optimizing the weights of the neural network instead of finding a general function of all the variables characterizing market information. And the approach for that is, again, it's a bit analogous to what they've done in the deep hedging paper, but we can use backpropagation. Well, we use stochastic gradient descent to refine the parameters, and we learn that, of course, to do stochastic gradient descent, you need the gradient, and the gradient can be found through backpropagation strategies. Okay, so yeah, so nothing irregular. I'd say it's like techniques we know to optimize weights of a neural network. We use stochastic gradient descent to optimize the policy or the function, and to get estimates, for example, of the current objective function with the current policy. We can simply use Monte Carlo, where we simulate many paths with the current policy, get estimates of the risk measure, the objective function, compute its gradient with the automatic differentiation package. And here we go. This is how it's done. Okay, so this is just a quick recall of stochastic gradient descent. So I'm not sure I have to go through this, but I'll go over it quickly. So stochastic gradient descent, basically you have a sequence of parameter sets that you hope converges close to the optimum value for the neural network. And on each time step here, the next sequence set of parameters is obtained by taking the previous one minus some learning rate times the gradient of the objective function, which is the risk of the terminal shortfall with respect to the various parameters. And as we said, to estimate these gradient, well, first the estimate of the value function itself without any gradient, we apply Monte Carlo methods, and thanks to the automatic differentiation packages, then we can obtain an estimate for the gradient. Okay, so this can be done through Python or other programming languages. Okay, so now we went into like a set of experiments to test the approach. So in the various papers, there are various experiments that are presented. Let's talk about the first one. So we hedge a two-month maturity put option with daily rebalancing with only the underlying asset. So we were only trading the underlying asset of the option to perform the hedge. We consider various levels of moneyness for the option: out of the money, at the money, and in the money. So we assume that the strike was, the initial underlying price was $100, and we considered various moneyness level. And for the first experiment, we use a regime switching framework to as the generating model to produce paths, which produces fat tails and volatility clusters, let's say, and other nice stylized facts for returns. So we did various sensitivity analysis to understand first, is that method robust? How do the various parameters or modeling choices impact the prices? So here, let's present the first set of results. So we did an analysis with respect, we used the CVAR as a risk measure for this first test, and we varied the confidence level. So we used CVAR at 90%, CVAR at 95%, CVAR at 99%. And here the first row is the prices obtained with this first risk measure, and these other rows here are the relative increases with respect to the price from the first row. So what we observe here is that the price is quite sensitive to the risk metric we're considering in this approach, because if we consider a 99 CVAR, 99% CVAR, we have out of the money option prices that almost double. So we see that this method is quite sensitive to the choice of risk measure we have, especially for out of the money option. For at the money, in the money, in relative terms, it's less sensitive because the denominator, I'd say, it's larger. but we see that the choice of risk measure can be quite impactful. And the reason for that is that if you look at a payoff option, the tail of the hedging loss for both position has a different profile. It's very asymmetric. So if you're hedging a short position, you have a much thicker tail than if you hedge a long position. So if you consider the price to be indifferent between both, this pushes the price up to compensate for the fact that the short position hedge is exposed to a very large tail. Okay, so the lesson from this is that the choice of the risk measure is very material if we want to apply these kind of methods. Okay, so now we wanted to assess robustness to the model specification. So if we consider various generating models, how are our prices impacted? Okay, so the various models we consider are the following. So we use CVAR 95% for this one, and we consider Black-Scholes-Merton, Merton jump diffusion, JGR Garch, and regime switching models. And Black-Scholes-Merton, so it's not complete because we have discrete timer balancing, but it's the amount of incompleteness is not very large in comparison to other models. And once again, we see that for in the money, at the money options, yes, there's some sensitivity to the model, but it's not that bad. But for out of the money options, these sensitivity to the choice of the generation model is very extreme. So some underlying models have very fat tails for the return, can have very extreme negative returns. So if you have out of the money option puts, you need to be compensated for that. So once again, we saw that the methodology is very dependent on the generation model you use. So based on this, we thought, well, okay, now we're using equal risk prices. What if we consider these prices to more common prices? So if we use common martingale measures or mean correcting measures typically used in the literature, how do our option price compare to this? Okay, so the idea here is that these, for the 4 generation models, generative models, here are the option prices that we obtain, and these are the relative increases if we use equal risk prices instead of risk neutral prices. And what do we observe here? Systematically, equal risk prices were higher than the conventional prices used obtained with conventional risk neutral measures, and especially so for out of the money options. Okay, wow, 203% increases. This means the equal risk price approach really pushes price up for these out of the money options. And again, this is due to what we explained earlier. The risk profile is very asymmetric when you use when you hedge a put option. If you hedge a short put option, you have a tail that is much thicker than for the long position. So the hedger, if we use that approach, needs to compensate it for that. So if we focus on the very far tail of the distribution when we consider risk metric, this pushes prices up. And at this point, we were a bit worrying, well, is this methodology applicable? Because if we tell people, well, your out of the money option prices are not priced appropriately, you need to increase their price by 230%. Like, I'm not sure people would necessarily listen to that. So we were wondering, well, are there ways to obtain results which don't lead to these outcomes? So we thought, well, because these are due to the very asymmetric profile of hedging losses and the very fat tail for the short position, maybe we could do 2 things. So the first thing we thought about is, what if we include additional hedging assets, such as options? So we use, for example, liquid short-term options to hedge a longer-term option. So that's the first thing we thought about. So so in this panel, again, we have out of the money, at the money, and the money, and we assume a Merton jump diffusion generative process. And we consider the equal risk prices if you have a daily underlying asset hedge, a monthly underlying assets hedge, or if you hedge with 1 month maturity options or 3 month maturity options. And what we were mainly concerned about here is the out of the money option. So if we use the framework we presented earlier, we had a price of 2.58, and now we see that if we use options as hedging instruments, this pushes the price down in the equal risk pricing framework. So we see that when we reduce market incompleteness by adding or taking into consideration additional hedging instruments, this normalizes price, because this lesser market incompleteness means lesser large tail exposure for the hedgers. So this has the effect of requiring less compensation for the short position and shrinking prices to, let's say, more natural levels that we're used to when looking at other typical pricing measures. The second thing we thought about is, well, perhaps we have these very high out of the money option prices because we're only looking at tail risk. So when we consider CVAR, we look only at the very far tail to price options. And so what if we consider not only the tail risk, but just regular risk? So we changed the CVAR for an expected penalty of the following form. So we use a quadratic penalty with an indicator if the loss is greater than 0. So it's kind of no penalty if there's gains, hedging gains, and a quadratic penalty if there are losses. So this has, we thought, the advantage of not only considering very far tail risk, but also more moderate level risk. So again, if we compare to the results we had, so same pricing, same framework, this is only with the underlying asset with the CVAR 95. This is, again, with the CVAR, but using the options that we just showed in the previous slide. And finally, this is only using the underlying asset through daily hedges, but changing the risk measure from the CVAR to the semi-quadratic penalty. And we saw that this had a similar effect to adding options into the scheme, meaning that when we consider more moderate risk, the more moderate risk is not as asymmetric as the tail risk for the two positions. So this has the effect, once again, of pushing prices back to more conventional levels. So the idea, or original idea of using only tail risk, maybe it's not good because the risk is so imbalanced that you have prices which are very far from what we're using to do. So if you consider instead more moderate risk, it's much less asymmetric between the two positions, and this has the advantage of reverting prices back to more conventional levels. Now, an interesting application of equal risk price is market consistent pricing of illiquid derivatives. Okay, so I know this is a topic where people are looking for solutions. If you have illiquid derivatives, an illiquid option, and you're trying to price it, it might not be feasible just through marking to market. So sometimes you need an approach to use market inputs, observable market inputs, and try to infer a price for that illiquid asset. And the idea here is that when you apply equal risk pricing, the pricing of such illiquid asset with optimal hedging carries over information from your observable hedging instruments. So you can show that, for example, if you use exactly the same framework for hedging, but you without changing anything about the underlying asset, but you push implied volatilities up, the price of your illiquid derivative will be also pushed upwards because they will reflect the dynamics of the hedging instruments. So if the hedging instruments are more expensive, the derivative that you're trying to hedge will also be more expensive when you optimize the hedging strategy. So this approach might be used to price illiquid options with liquid instruments because it allows carrying information from observables to your unobservable derivative that you're trying to price. So that might be an interesting application of the scheme, because if you're pricing liquid derivatives, well, you don't need a model. You just need a mark-to-market or like a implied volatility surface. But I think this potential has the most, this application, sorry, has the most potential for illiquid derivatives. So I'll conclude my talk on that. So we proposed, well, we adapted the original equal risk pricing framework to price derivatives, and we saw multiple advantages with this approach. So first, the price of the derivative is consistent with optimal hedging strategies. There's a unique transactional price for both the long and short positions, unlike some utility indifference framework. The price is under certain conditions. We haven't talked about it here, but in the first paper, we show that under certain conditions, prices we obtain are arbitrage free. So that's another advantage. And finally, through this epsilon metric we discussed about, we're not only able to price derivative, but we're able to measure the extent to which a market is incomplete. So as a byproduct of this method, we can measure how hard it is to hedge in a given market. So once we set up the theoretical setting, we show that the calculation of these equal risk prices is feasible through, I'd say, conventional reinforcement learning approaches. So for instance, we use deterministic policy gradients, a bit like in the deep hedging paper of Euler. And finally, we did some sensitivity analysis, and we found that the prices can be quite sensitive to the choice of risk measure or the choice of hedging instruments. So we need to be careful about selecting these when we apply the framework. So I'll finish my talk here, and I'll be open if there are any questions about that.